So we now continue regarding recursion. So far, what we have seen is while it's a very powerful technique, in fact, one of the most powerful techniques to code, it can be quite inefficient if not implemented correctly. Okay, so let's look at a very important example, and that is the binary search. What is a search? You have a certain value. You want to see whether it occurs in a given list. Okay, that is a search. Python's list class already has a search. It is a sequential search. What is sequential search? The program starts scanning from the beginning of the list until it either finds what it is looking for or reaches the end of the list and reports a failure. So you have a list, you have a value. Python is going to check whether it is this first item or second item or third item and so on until the entire. Notice this is an inefficient way of checking, because if your list has 1 million terms, you are going to make 1 million checks before you report a failure if that element is not. So it's quite inefficient. Okay, so there has to be a better way. Well, what if your list were sorted? Okay, sorted means arranged alphabetically or numerically, whatever be the type of your list, right? Example, lexicon is a list of strings. Lexicon means actually a list of allowed words for your language, right? So for an example of lexicon is your Webster dictionary or the Oxford dictionary, or in any other language the dictionary you may actually use. So how do you search for a word in your dictionary, right? You know where to find your word because it's alphabetized. Okay, so you alphabetize it or maintain a sorted list. In binary search, what do we do? So you have a list, maybe short, maybe long, and you have an item. You want to check where that item lives. You aim it right in the middle of the list. Middle. Okay? If our target value is not right in the middle, then it's either less than the middle term or bigger than the middle term. So it is in one of the two sublists, one on the left and one on the right. In other words, the search now proceeds to one half of the half list and we repeat with recursion. The advantage of the binary search in comparison to the sequential search, this should be a search, is that binary search is much faster because, say you had a long list, now you have half the size of the list to worry about. Okay, at every stage you're only looking at half the list. Using binary search on a list of length n, we obtain a result within log base 2n number of steps, whereas the sequential search can take up to n steps. Okay, so here is an implementation. So let me remind you, if the recursion is not implemented well, then you will most likely have an inefficient program in your hands, right? So here is an example of a bad implementation. Let's understand the implementation first. My function is called search. It has two parameters. One is lexicon, the other is your target. If the length of the lexicon is 0, then return false. That is the base case. Okay. Otherwise, your target, you want to check it with the middle term in your lexicon. So find the middle index, mid index. What is it? It's length of lexicon, floor division by 2. So if your lexicon has 5 things, 5 divided by 2 is 2.5, but the floor division is 2. You see? So you're looking at the floor division. If your lexicon has 6 things, then floor division is division by 2 is 3. That's fine. Now, if your target, the guy you're looking for, is the middle index item in your lexicon, then your search is successful. Return true. That is, you found it. Otherwise, the target is less than the middle index item, in which case start searching until middle index, from the beginning until middle index. So first half of the list. If it is not equal and it is not less, then it has to be greater. So start searching the next item after the middle index term and until the end. Okay, so this looks like a reasonable application of your binary search. What could possibly go wrong? Let's look at an example diagram. You're searching for F in this list of letters. F, so there are 6 things. 6 divided by 2 is 3. So F compares with index 3 item. 0, 1, 2, 3. F compares with I. F is not equal to I. In fact, F is less than I. So now we are searching in the first half of the list. There are 3 things. Floor division of 3 by 2 is 1. You see, 3 divided by 2 is 1.5. Floor division is 1. 0, 1. So F compares with E. It is not equal to E. In fact, F is bigger than E. So now we are looking in this half. This has only one thing. So floor division of 1 by 2 is 0. Okay? 0 item is G. F compares with G is not true. So F is smaller than G, so it now looks at the first half, that is the empty list. When you have empty list, that is length of lexicon is 0, you're returning false. So you return false, false, false. So why is this not a good implementation? Because the recursion relies on creating a new list, which is half the original list. So notice you started with this list, right? And now you created half the list, and then another half the list, and then another half the list. So creating the slice takes time proportional to the length of the slice. So in other words, you have ruined the benefits of binary search. Binary search algorithm was meant to reduce time in search algorithm. But if I keep creating list again and again, then I have wasted my time in that creation. So this is not a good implementation, although it is a very useful implementation. I have uploaded that inefficient search tracing, so you can check it with tracing. Where did it go? There you go. Okay, you can run it. All right, so now let's run this search function. So notice there is a print statement that will give you the tracing of your code. Okay, so I'm searching B E G I N S. Oops. That is my list. I'm searching for letter F in this list. Okay. With this print statement, I will be able to trace how the algorithm goes. Okay. So, all right. So F, that's my opening command. Then it's going through BEG. Then it's going with G. Then it's seeing the empty and then returning a false. All right. So this is a little inefficient because I'm rewriting half the list again and again. Next video, let's look for a more efficient way of doing the same code.